And if we do, then we'll go on and do a little bit more stuff. Does that make sense? I just want to keep cruising through this as efficiently but thoughtfully as possible, because the faster we go through it, the faster we can get to review, and that's good. Before we do anything else, though, I need to talk about the final real quick, because I was just looking at the calendar and realizing that what I told you is not quite right. So we had been talking about the AP Physics final, doing it either on Tuesday, April 28th, from 1 to 4, or Wednesday, April 29th. And for some reason, I was thinking that that was a teacher-directed day, and it's not, which means that I have the lovely opportunity of going to East High School and meeting with the other physics teachers, which is indeed a nice thing, but it does mean that I'm not here at 1 o'clock, which is when I had thought we were going to do our test. And I'm really, really sorry about that. I really thought that that was going to work, and then I looked at the calendar, I'm like, oh wait, that's not going to work. So I'm going to move that one back. I'm going to sneak out a little bit early and do that from 3 to 6. And I'm really hoping that doesn't totally mess with people's plans. If it does, if you were, like, if that time on that Wednesday worked and now this is not working for you, then please talk to me and we'll find another option, okay? I'm really sorry, and I just realized it, and I'm feeling really dumb about it, but it just, you know, things happen sometimes, right? Like, you forget to look at your calendar all the way through. So anyway, those are the 2 times for finals. We'll probably, I'll probably send out send around a preliminary sheet next week just to figure out kind of what we're talking about numbers-wise, how many people are going to be in here each block. Does that sound, or each time? Does that sound okay?
That Tuesday is an 8 right? So
that Tuesday is the weird day that is not a day when juniors have the wonderful opportunity to take the ACTs.
Oh.
So for the juniors, they will be testing in the morning that day. And nobody else has school that day.
Yeah.
So that day would be, and my understanding is that they would be done by 1 o'clock. Not that, my guess is that most of the juniors will not sign up for that day, but maybe they will because they just like to test and just get it done, you know. So those are the 2 times. Does that make sense to everybody? Like I said, if I just totally threw a wrench in your plans, then please come talk to me right after class. We'll figure something out. We'll be able to do it. I have to go to my district meeting, so that is what it is. Does that sound okay? All right. So notes out. Here we go. I was able to get so the reading is up, the homework is up, the homework you picked up last time as well. Is that right? And I wanted to ask you a logistical question. I asked the class yesterday about this as well. I totally slacked off and didn't get your rotation tests graded, but they are graded now, and I'll put them in Infinite Campus, maybe right after school, and if not, then I'll put them in this weekend. My question for you is, so I'll put them in Infinite Campus so you know your score regardless, okay? I just want to make that really clear. I can hand them back, like, next time I see you, or I can wait and I can hand them back when we're in full review mode. It does not matter to me. I'll tell you that the other class that I asked said, let's just wait and do it when we're in review mode, when we're actually thinking about that stuff again, and you know what I'm saying? Because we'll go through it and answer all the questions and all of that. Is that okay with you all?
Yeah.
Okay? If you really want to see it ahead of time, you can come in, certainly. But I just feel like let's get this stuff done and let's stay focused on this. Does that sound okay with people? Okay, I just don't want you to think that I'm like withholding information from you or something like that. Okay. All right. Here we go. So this is in the reading that you did. This is chapter 22. And I'm kind of going in the order that is in the book and kind of just in the order that makes sense to me. Some of this is stuff that we talked about last time, but I want to make sure that you have it written down and that it makes sense and that you have opportunities to ask questions if they come up. So when we're talking about basic circuits, like the circuits that we built last time, okay, there are 2 really, really important definitions. The first one is current. Okay. Does anybody remember what current is? This is your answer. Go.
Is current? If electricity going through a wire is like water going through a pipe, is current similar to the water pressure? Or am I thinking of one of the other two?
You're thinking of one of the other two.
Okay. I
What
think
is-
I know which one I was thinking of then.
What is it, dude?
I was just going to say flow of electrons.
Yeah, it's flow of charge. Flow of charge over time.
Hi, Schoenberg.
Okay.
I was just looking to see if you were free. I'll check you out.
Are you?
I'm here
Can
for
you?
a while after school.
Can I call you in a little bit? Because you have 8th graders, right?
No, just 5 of them. So
Okay, I'll call you when we're labbing.
okay.
Thanks. All right. Flow of charge per time. Anybody remember what letter we use for current?
I.
We use I. Jonathan needs to raise his hand so that everybody else gets a chance to answer too. I is what we use for current. What do we use for charge?
B.
No.
Oh.
Q.
Just kidding.
What do we use for time? Yay! Okay? So current is charge per time. Literally, that's what it means. We measure it in what?
Ohms.
No! She needs to start thinking before she speaks. Ouch! Measured in what?
Big O for 4.
Amps. Amperes. Amperes is the formal way we usually say amps, and it's marked with the letter A. Okay? If we draw ourselves a nice little simple circuit, what is that? The battery. And what is that? The resistor. And then I put some wires there, right? That's a nice little simple circuit, kind of like the one that you're going to build when you use the meters today. Okay? We kind of talked about this last time, but I don't know that we actually defined it. Which way do okay, so we said that the electrons are the things that are flowing, right? We talked about why that was true. We got the nucleus in the middle. The nucleus doesn't go anywhere. It's those valence electrons that are moving. Okay? Which way do the valence electrons go in this picture? Down. Well, to the right. Yeah, somewhere. They have to go to the right at some point, right? And the left later, right? Yeah. Let me tell you. Electrons will flow from the negative terminal of the battery to the positive. So the electron flow goes in this direction. The little side is the negative, the big side is the positive. Okay? Now, I need to say a couple of things about this. We're going to talk about batteries in a minute, but I want to make it very, very clear. When you buy a battery, you're not just buying a container of electrons. Okay? It's not just a container of electrons, and as soon as all the electrons have gone, then you're done. That's not what it means. A battery has a chemical reaction going on in it, right? My chemists know that. You guys have studied the chemical reaction that happens there. Okay? There's a chemical reaction that gives electrons. You didn't talk about this in chemistry?
For like one day right before the end.
Oh, well, one should know if one is in chemistry that there is a chemical reaction that happens in a battery. That's as much, as a physicist, that's as much as I'm going to tell you. Okay? Just know that there's a chemical reaction that happens in here. As a physicist, that's all you need to know in this class. Okay? So, what I need you to know is that this is not just a container of electrons, right? Like, how many electrons are left? No. Okay? When I close the switch, let me put a switch in this because it makes it more fun. That's a switch. Can you tell? It's open right now. Okay? Are the electrons moving right now in this picture?
No. Oh, okay.
Are the electrons moving? Yes, they're like the 7th graders in the gym, right? They're bouncing out. How do you know they're moving?
It's above absolute zero.
It's above absolute zero, right? If it's absolute zero, then they're not going anywhere. But of course, it's above absolute zero, so they're just bouncing back like this, right? As soon as I close this switch, well, let me ask a question before I close the switch. Are there electrons right here?
Yeah.
Yeah, because that wire is made of copper, and copper is made of protons, neutrons, and electrons, right? Are there electrons right here?
Yes.
Yeah. Are there electrons right here?
Yes.
Yeah, there are electrons everywhere. Hold on, just let me draw some electrons real quick, David, and then I'll answer your question. So there are electrons here, and here, and here, and here, and everywhere, right? They're all over. And let me ask this question real quick, and then I will answer your question. Is that fair?
Yeah.
As soon as I close this switch, what happens to those electrons? What do they do? We talked about this last time. What do they do? Yeah. Yeah, they flow in the general direction of negative positive. That doesn't mean they like stand up and start marching, right? But they are moving in this general direction. We would call that, looks like counterclockwise, yeah? Okay? So as soon as I close that switch, not only are the electrons hanging out here going to move, but the one that started here is going to move. And the one that started here and here and here, all of them are moving in that general direction. Is that okay? Every single electron that's a valence electron, not every electron, but all the electrons. It's not just that they start here. That's the thing I really wanted to make clear. Yes? Sorry about the long pause before I answered your question.
Kind of answered it a little bit. But so if there was like a light bulb, why would it not light up before you close the system if there are already electrons in it? Just because they're not like moving in a general direction.
Okay, so I have a light bulb, yeah?
Yeah.
Oh, here's a light bulb. Why isn't it lit? That's what you want to know, right?
Yeah.
There are electrons in it. Would you all agree?
Yes.
Absolutely there are electrons in it. Why aren't they, why isn't it lit?
Because there's no like flow, I guess, intake of more electrons. I don't know.
Kind of, yes, go.
Well, isn't it like electrons moving through the wire that creates like the friction, which makes it go like that?
Yeah, that's a good way to, yeah, I mean, yes, I wouldn't say like 100% that's perfect, but that's on the right track. So we're kind of going out of the order that I had it in my head, but that's totally fine because I like this order too. So a battery provides electrons with potential energy, right? I think we talked about that last time. Just like I provide the frog with gravitational potential energy. Do you remember talking about that last time? Right? I keep picking the frog up. I keep doing work on the frog. I keep giving him potential energy. So the battery gives electrons potential energy. And then lets them go. And those electrons are going to fall, in quotation marks, right? Because when we think literally, it's like, oh, they get all stuck down here. No. They're going to fall around the circuit. But unlike the frog that accelerates downwards, the electrons lose almost all of their energy, that energy that they were given here, right here. They lose it in the form of heat and light. Does that make sense? Okay. So why aren't the electrons in here glowing?
Because they don't have any energy.
They don't have any potential energy to give off. Yes. That's it's a really good question. Is that okay? Okay. Other questions that arose from that, or are we okay so far? Okay? Okay. So I'm going to confuse you again in just a second, because that's my job. Okay. Let me make sure that I got all that. Okay. Boop, 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 boop. Okay. Now, we said that David said that current was the flow of electrons, right? So here's the problem with that statement. Oh, you're not like ripping everything apart. Dang it, I'm done! No. So they had electric circuits long before we knew that electrons existed. There were scientists that were studying electricity and making things spark and watching lightning bolts happen and making lightning bolts and lighting up things like light bulbs and things like that way before they had any idea that an electron existed. And I don't know if you've heard this before, but you guys have all heard of Benjamin Franklin, right?
Oh, yeah.
Whether it's in history class or in science class, because he was one of those Renaissance people who did all kinds of things. Okay? He studied a lot of electricity, and he is the one that I blame with screwing it up. Okay? You know, when we were talking about like charging things, you know, like you, and then you go to your little brother, you're like, right? Is there any way for me to know if I have a positive charge and I'm going to impart that or a negative charge? Do I know?
No.
All I know is that I have an excessive charge, right? And maybe I can charge something else opposite. So I know that there are two charges. I know that much. And I know that they're opposites. But somebody had to call one of them positive. Say, when you have wool socks and you walk on your carpet, that gives you a, you got to call it something. We call it Larry or Joe or negative. Okay? And the opposite one, we could call Sally or Sue, or we could call it
Negative.
positive, because I said negative the last time. Put your calculator away so you can listen and then you'll get those right. Okay? Somebody had to decide that. And from all the stories that I've heard, it was Benjamin Franklin who decided that. He had a 50-50 shot. And he screwed it up. Dang it! Dang it! He screwed it up. He said, I'm going to call this thing negative. But we talk about positive charge flowing. So way before we knew that electrons existed, people had studied current and they'd studied circuits and they had decided that current traveled from positive to negative. Now we know that that's wrong. Now we know that it's actually electrons, right? Because we understand what's going on. But back in the day, we had no idea. And so they used to call this current. Now, I like to call it conventional. I put it in quotes because it's kind of silly. I'm going to call it conventional current. Okay? And this conventional current is the current that we talk about. It's technically a flow of positive charge, okay? And that positive charge always flows from the positive terminal to the negative. So again, he had a 50-50 shot. He screwed it up. But, you know, it's not like we can say anything to him now, so I guess it's okay. Whatever, like, guess we have to live with it. Every year people are like, well, why don't we just change it? Right? Like, now we know more, why don't we just, it's just one of those things. Like, people have been doing this for so long, like, I don't know why we don't change it. I guess if you wanted to start a revolution, you could, but probably people wouldn't listen to you. Maybe other physics students in high school who get cranky about it too. But most of us now, yeah, we're just like, okay. So we know the current goes this way, and that's the flow of positive charge, even though there really isn't any positive charge that's flowing. But what I need you to know is that the electron flow is in the opposite direction from current. It's annoying, it's counterintuitive, and you can blame Benjamin Franklin.
Sweet.
That's all I have to say. Fair enough? All right. Last comment about current, then we're going to move on. Questions before I keep going?
That's like Newton. So that's two scientists you don't like.
Oh,
You
yeah.
don't like Benjamin and you don't like Newton.
No. It's true.
Some of the best like
Are there any
brands in
you
the world.
like?
There are a lot of them that I don't know anything bad about, and so I don't have any reason to dislike them, so sure, I like them. Right?
Are there other ones you don't like?
Those are the two that I have like the biggest beef with. Yeah. I'll keep you posted if I learn other things, but yeah.
You need to have like a weekly or a monthly newspaper that goes out.
Right? Cranky pants about da-da-da. Yeah. What's
A
that?
newspaper at Central would be awesome.
It would be. Somebody needs to get on that. Not me. I don't have time for that. All right, last question I have for you.
So solid.
Right? Get it right.
Maybe actually do something.
How fast do electrons move around a circuit? So I close that switch. How fast do they move? I get a little radar gun and I start clocking them. How fast do they go? You gonna give a guess?
Super fast.
Super fast! That's a very technical answer. They go super fast. What does super fast mean?
Speed of light.
Speed of light, he says. Why do you say that?
Because it's Superman.
They're electrons. They're not superheroes.
They go fast like Superman.
How long does it take for the light bulb to light up as soon as when you close that switch?
Almost instantaneously.
It happens really fast, right? It's not like it's like wait. 1,000, 2, no.
Sometimes you do though. There's some
Yeah, if the
people
circuit's
are
bad.
right,
Yeah. Or like we got new light bulbs in our kitchen and they're not incandescent light bulbs like this, and so they do take time because they have to heat up, right? Like they're yeah. But a nice little incandescent like one like these. How long does it take between the time that I have it hooked up and the time that it turns on? It's just like there, right? Like I did it. Oh. Right? Like it doesn't take any time. How fast do those electrons move?
Super fast.
Super fast, he says.
Super fast.
This is how super fast they move.
What is that? Was he good?
No, I doubt it's pretty good. But it made a lot of money. So it was, the other ones were bad. This one was
All right, River.
Sorry.
Super fast. Take a look up here. Is that super fast?
No. It's fast for them.
I guess it's all relative, right? So 0. And this varies depending on the type of wire and blah 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 blah. But this is like a value that is reasonable. So that's
Wow, that's kind of slow.
super slow, I would say.
Yeah, super slow. That's not super fast. It's like super turtle.
Like super slow, right? So we're talking about 9. So that's what? That would be 0.00000. I gotta make sure I do that right. Yep. 93 meters per second. Or if we look at it just in terms of centimeters, like that's like wow.
Super slow.
That's not very fast. So my question for Will then is, if they're moving that super slow, I sound so cool today. I have to tell you. Why does the light bulb light up so fast?
Because there are a ton of electrons, like a lot of them.
There's already electrons within the wire, and you're just
Right.
So they're like are all over. So it's like
They're like everywhere. Like, get away! Oh, there's one there. Yeah. Right. When they close this, there's already an electron there.
Yeah.
And as soon as that's closed, now those electrons, because of the battery, have energy to give off. Okay? That does happen super fast.
too fast.
Okay? That imparting of energy happens at the speed of light. We establish that electric field at the speed of light. Okay? But the electrons themselves
Super slow.
really slow. Remember, it's like those, I was telling you about the 7th graders, right? Like the 7th graders walking to the ice cream. Did we talk about this?
Yeah.
Right? So like they bounce around. I mean, it takes them forever. Have you ever watched middle schoolers like try to get from one class to another?
Oh my
They must
God.
have like 10-minute passing periods. I don't know how they get from one room like to the next room over. Because they and eventually they get there. It's not even like they've gone anywhere else, just like from here to here. It's ridiculous. Ridiculous. Yeah. That's what these little guys are like. Super slow. We okay? Do you have a question or are you just stretching? Okay, just want to make sure. All right. That was one word. Let's do the next word because I've promised you that I was going to be done talking about 15 minutes ago. But I blame River. Okay. Next word. Voltage. What's that? Did you have a question?
I think that this is the one that I was thinking of earlier.
I think it was.
Because the third one has no. Because the third one is what's trying to stop the electrons from getting through.
Okay. Okay, let's go. So voltage. When I close that switch, the electrons move. You agree?
See,
They don't move fast, but they do move in a general direction. Okay? Why? Why do they start to move in some general direction? What do they have to feel? a force, right? Okay, the bouncy, 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 whatever, like there are forces involved there, but we don't really care about those right now. Okay, the reason that they start moving in that general direction is because they feel some sort of force pushing them that way. Okay, that force comes from the battery, from the voltage. So we're going to say that those electrons move because they feel a force. Okay? It comes from a thing that we call an electric field. And this is that stuff that I'm not actually going to teach you because it's not stuff that you actually have to know, but I'm just going to tell you that it exists, kind of like the gravitational field that I mentioned last chapter. Okay? They're kind of the same thing, and I just want to put that out there, but I don't want to really get into it. So I'm just going to say, whoa, that's a weird thing. Okay? That electric field comes from that silly battery. Okay? We said this already, but I just want to make sure that we've got it all in our notes too. Okay? So the electrons fall around the circuit just like the frog falls. Okay? They fall in the direction that they feel the force. Okay? And like the frog, they convert their potential energy. What kind of potential energy do electrons have? Electric potential energy, right? Okay. That electric potential energy is converted into what? Is it in the I mean, if it had lots of kinetic energy, that means it'd be going fast, right? These electrons aren't moving very fast. What is that? What is the energy converted into for potential?
Kinetic.
No, not kinetic. What is it converted to, friends? We just said this.
Light and heat.
Light and heat. Yeah, this thing lights up, right? Okay. So the electrons that are down here and this part down here all have pretty much the same amount of potential energy. They lose like a minuscule amount, like so small we're not even going to count it. Here. They lose almost every single bit of their energy right here. And then lose just a little tiny bit down this strip here. Okay? So they're going to lose most of their potential energy to light and heat, okay, in the light bulb or in the resistor. Is that okay? The voltage comes from the battery, okay? And the thing that the battery does is that it gives some, so I'm going to say it provides that electric potential energy per charge. That is the voltage. Voltage is P sub E divided by Q. Okay? This is voltage. What's it measured in? Volts. Let's do the V also. Okay. Sometimes instead of the word voltage, there are other words that will be used. The one that I want you to be most aware of is a 3-letter acronym, EMF. I'm not even going to tell you what it means. I'm not going to let you worry about it. I just want you to know that if you see EMF in your head, you can translate that to voltage. Okay? So if you see EMF, just say voltage, and you'll be fine. Is that okay? All right. One more thing, then I will let you lab, I promise. And that's the cause and effect story when we put these two things, this current and this voltage together. I'm going to go back to I'll just draw a new one. New battery. Do you want a light bulb or a resistor? Daisy, what do you want? Resistor, she says. With some element of certainty, right? Okay. What causes the electrons to move? What causes them to move? I've only asked you this like 3 times today. A force. Where does the force come from? The battery, right? I'm going to keep asking you this from now until May 7th until you answer it every time. What causes the electrons to move? A force. Where does the force come from? Okay, this is what I'm talking about. So there's a cause. The cause is the battery or some voltage source. Okay? The battery creates a force that pushes on those electrons. It provides potential energy, electric potential energy, to the electrons. Okay? As a result of this force, what happens? Not a trick question. Current happens, right? Okay? The electrons move. So the effect, do you remember doing cause and effect stories like when you were in kindergarten? This right? This is that kind of thing. The battery is the cause, and the electrons moving, I'm going to say in a general direction, because I don't want you to get mad at me and say they always are moving unless it's the absolute zero, Miss Garbling. I know. Okay? Which is that current is the effect. As they move through the resistor, they're going to lose electric potential energy. Okay? It's converted to heat and light. Okay? In the resistor primarily. If we think about it, the more energy they have, does it make sense that if they have more energy, they're going to move more rapidly? Does that seem to make sense? Yeah. Okay. The current is proportional to the voltage. As the voltage goes up, the current's going to go up. Could you put your phone away, please? Thanks. But the current also depends on what else is in the circuit. Okay? Depends on the size of the resistor. Whether that's an actual like resistor, if it's a toaster, or if it's a hairdryer, or if it's a light bulb, or if it's a whatever, okay? It depends on the size of the resistor. Oops, I don't need that. There we go. Okay? And we measure the size of the resistor as the resistance. I know, right? Resistance is marked with the letter R, and resistance is measured in, does anybody know? Mira knows this one. She said it out loud earlier.
Yeah.
What is it?
Ohms.
Ohms. Yeah. Ohms is marked with the capital letter omega. So we know a little omega. We've been playing with that one for a while, right? We're using the capital letter omega now. Okay. Just thinking logically, if the resistance goes up, what do you think is going to happen to the current? It's going to go down. Doesn't that make sense? Right? If the resistance is something, it should seem pretty logical, I hope. Okay? So if R goes up, I is going to go down. So if we were going to write down a thing, so we've got this one here, I is proportional to V, what would we say for I and R? What? Say it like you mean it, because you know this. We've been talking about this for a lot of days lately. If one goes up, the other goes down. What is that? What kind of a proportion is that? It's inversely proportional, right? Do you know this? We've talked about this, haven't we? Yeah. So I is inversely proportional to R, and I is proportional to V. We said that a minute ago. So we can put those together, and I equals V over R. This is the cause, and this is the effect. Okay. Often we will write this like that. I think it's one of those fear of denominators issues. Okay. This thing has a name. It's called Ohm's law. And that's what you're trying to prove today. Okay. So you're going to get out some equipment. You're going to go to your meters. Take a deep breath and talk to your partners. And if you need help using your meters, you let me know. You use 3 different resistors, 4 different voltages per resistor. Measure the voltage, measure the current. I've got some graph paper right up here waiting for you to graph on. Okay? That's what you need to do today. Sound good? Make it happen.
That's it.